Hey again. So this is the third video of a series of videos I'm making about how I compile regular expressions from my adaptive radix tree. Um, this part, we're going to talk about how you take the intermediate result and serialize it into a pattern string that will work with any of the major regex engines. So you can actually use it to start matching stuff. So this compilation result, this you can see up here, this dot result equals result in the constructor. This is what we get from the two regex function we talked about last time. And it has this serialize function. What the serialize function does is it walks the tree structure that's stored in that this dot result property. And the way that I do it is with a stack. So what I do is I have this thing called a pattern array that I start right at the top, and I know that right at the beginning, at the root of the intermediate result tree, I'm going to have a group. So I start out the group at the beginning of the pattern, depending on whether it's a capturing group or a non-capturing group. If it's a capturing group, then it's just a plain parenthesis. Otherwise, it's the one with the question mark and the colon. And then we have a stack for keeping track of the traversal. And um, yeah, so pattern array. And then you can see at the end here, in the pattern array, I'm just joining all the tokens in the pattern array with an empty string. Okay. And so that's basically how it's working. So as long as in the first value in the stack at the 0th index is null, and so that's just a convention that I follow. I find that makes it easier to reason about stack-based traversals. So that's how I often do it, and so that's why I put that there. And we have an object with three properties: iter, type, and opt, that help us understand something about the group, right, that was returned from before. And so we're going to get into this traversal, and basically, um, while we have a value that's not null at the end of the stack, they're going to grab that tail result, that tail object at the end of the stack, and we're going to call its next method. If it's done, then that means we need to close. We need to put something in the pattern array, a token that represents like the end of the group, okay? And so we push either a closing parenthesis or a closing parenthesis with a question mark after it. And when do we put one with a question mark after it? Well, that means it's an optional group, okay? So if the result is optional, okay, if it's one of those optional groups. So and then we pop that value off the stack because we want to go back up in our traversal. Otherwise, if the result from that iterator is not done and we have a value, then we take a look at that value and we check what it is, if it's a capturing group, non-capturing group, or byte stack, okay? And if it's a capturing group, then we push just a plain parenthesis onto it. If it's a non-capturing group, we would do the parenthesis question mark colon. And then after that, for either groups, we basically push onto the stack another object that has those properties, iter, type, and opt, okay? So you see what we're doing. And for byte stack, what we do is we go to the pattern array, we take the tail thing on the end of the pattern array, and we check that the tail item is not null. If it's not null, and at the end of the pattern array, and if it matches a regex pattern. See, this is where it gets a little bit boring because my serialization logic, it works with the intermediate result that I'm producing. This logic is a little bit fragile. If you want to do all kinds of optimizations and stuff, you might need to write your own serialization logic. But I'm using a regex pattern in order to check whether the last element, the last token, is an is a is the start of a group. Okay, um, in particular, it's there's a exclamation point there. So if it's not the start of a group, okay, if it's not the start of a group, in we have a byte stack. Okay, then we put a pipe. All right, if it was not this, if it actually is the start of a group, okay, so a parenthesis maybe followed by a question mark and a colon, then we wouldn't want to put a pipe there, because then we're going to have a pipe right away inside of our group, and we don't want that. So that's what that line means. Um, so then we're going to ask for we're going to get all the code points by from each of the values in the byte stack by iterating. And this you could customize. Okay, I'm supporting limited ranges of code points as um, literal characters in the regex pattern, and every code point outside of those ranges, those alphanumeric ranges, I'm just making the hexadecimal representation of that character. You could be more liberal than that, but I was just being very conservative and a little bit lazy. But if you want even more compressiveness, you could customize that, just as long as you keep in mind what the rules are syntax wise for the different regex engines you're working with. And so we push that onto the pattern array, and at the end we join it, and that's it. That's how you compile the regex patterns from an adaptive radix tree. You can make massive ones. So in closure, I will say I have other videos where I demonstrate compiling profoundly massive regex patterns from Moby Dick and the complete works of Shakespeare that recognize every word in those texts. Okay, so this thing really works. It's really cool. Those are kind of like some fun examples, but the truth is, I've written regex patterns professionally, um, and I have like a knack for it. But despite that, there are some situations where you can't possibly generate them fast enough. It's hard for me to explain because it depends on the scenario that you're in, but there are some scenarios in the engineering world that you can find yourself in where the only way to solve the problem is producing the pattern fast enough, the patterns, fast enough, and from such a large body of input strings, this is the kind of scenario where that would work, okay? Um, so there really are use cases for this kind of compiling. Um, and obviously, if the strings that your options are right for your regex pattern, if they have shared prefixes, even better, because it's faster with the radix tree, and then it has the prefix optimization and the regex pattern, and it's great. So, anyways, you don't have to. I'm not doing the full range of possible optimizations, but I do have this. Obviously, now I'm showing you this in multiple stages. So you have the toRegex function that gives you an intermediate result, and then you have um, that that intermediate result that you walk to serialize into a pattern. So you can kind of sneak in there and implement your own logic if you really want to. And I use a Latin 1. I made a collation for Latin 1, so you don't have to use that. Like I said, you could use any collation mapping logic that you want. The only restriction is really that you have to be able to map you have to be able to map your code points. You know, you have to have like you have to be having code points only like 255 up to 255 values, right? That's the size of your alphabet. If you have to match strings that are actually really using more than 255 code points, then this kind of tree data structure might not work for you. Okay, um, so but I think that's probably a very rare situation. Um, you might say like, well, what about UTF-16? Okay, not everything is Latin 1 or ASCII. See, that's not what I mean. I'm not saying how many code points are supported by the character encoding that you're using, like UTF-16 or whatever. I'm saying the actual body of text that you're working with. Okay, the actual texts that you're working with that you need to derive regex patterns from. How many unique code points are actually being used? Because I think very rarely you would find that you're consistently, using more than 255. Like I said, if you are, then this may not work for you. But if you are, then this will work fine because you just have to come up with your own mapping in order to get them into the tree, and then after with your pattern to remap code the hexadecimal or whatever else you have in your pattern appropriately. So um, I give Latin 1 collation because it's commonplace. It's kind of versatile, but you don't have to use that. You could use any kind of mapping with this tree. So, anyways, thanks for watching. I hope you find this useful.